Hi, I'm Anthony. Today our topic is a complete guide to AutoKeras. In the beginning, we will discuss about neural architecture search, NAS, and some of its searching strategies. Then, have an introduction to the search strategy called Bayesian optimization, BO. Next, we will check some technical details of AutoKeras. In the end, I'll introduce the open source tool AutoKeras and provide two NAS examples based on this AutoML solution, and make a remark on AutoKeras. Deep learning has remarkable progress on various tasks. One crucial aspect for this progress are novel neural architectures. Most of the network architectures are developed manually by human experts. The process of network development is time-consuming and it involves a lot of human instinct and heuristics. So there's a rising demand of automating this process to reduce human intervention and improve model performance. Neural architecture search, NAS, is a process of automating architecture searching. Recently, NAS methods have outperformed manually designed architectures on tasks such as image classification, object detection, or semantic segmentation. Here is a graph to illustrate the process of NAS. First, we define a search space. Search space defines which architectures can be represented in principle. Prior knowledge might be helpful to provide a better search space and reduce the size of search space, but this may also introduce human bias and prevent finding novel architectures beyond current human knowledge. Next, we use a search strategy. Select an architecture A from this predefined search space. Search strategy details how to explore the search space. It tries to find well-performing architectures quickly, while preventing premature convergence to a suboptimal architecture. The architecture then passed to a performance estimation strategy. The performance estimation strategy then feedback the estimated performance of A to the search strategy. Many different search strategies can be used, including random search, Bayesian optimization, evolutionary methods, reinforcement learning (RL), or gradient-based method. Evolutionary algorithm has a long history in NAS. Many neural evolutionary approaches use genetic algorithms to optimize both the neural architecture and its weights. However, when scaling to contemporary neural architectures with millions of weights, SGD-based weight optimization methods currently outperform evolutionary ones. Therefore, more recent neural evolutionary algorithms use gradient-based methods for optimizing weights, and solely use evolutionary algorithms for optimizing the neural architecture itself. Evolutionary algorithms evolve a population of models. In every evolution step, part of the population are sampled and served as a parent to generate offspring by applying mutation to it. In NAS, mutations are local operations, such as adding or removing a layer, altering the hyperparameters of a layer, adding skip connections, and so on. After training the offsprings, their fitness or the validation performance is evaluated and they are added to the population. Reinforcement learning (RL) is also commonly used in NAS. One way to frame NAS as an RL problem is that we're considering the generation of a neural architecture to be the agent's action, with the action space identical to the search space. The agent's reward is based on an estimate of the performance of the trained architecture on validation data. An alternative setup of RL in NAS is a sequential decision process in which the policy sample action to generate the architecture sequentially, and the reward is obtained only after the final action. Since no interaction with an environment occurring during this sequential process, this simplified the RL problem to a stateless multi-arm bandit problem. Bayesian optimization (BO) is one of the most popular methods for hyperparameter optimization (HPO), and it is also used in NAS. Typically, BO tools are based on Gaussian process and focus on low-dimensional continuous optimization problems. Therefore, many modifications are developed for NAS. Some works derive kernel function for architecture search space in order to use classical Gaussian process-based BO. Some use TPE or random forest to search high-dimensional conditional spaces. Here, AutoKeras use Bayesian optimization as a search strategy, and we will go through an introduction to Bayesian optimization in the next section. Bayesian optimization is a global black box function optimization. It builds a surrogate for the subjective and qualifies the uncertainty using Bayesian machine learning. Bayesian optimization consists of two parts: surrogate model and acquisition function. The most commonly used surrogate for Bayesian optimization are Gaussian process, random forest, and tree structure Parsons estimator (TPE). There are many different acquisition functions like expected improvement (EI), upper confidence bound (UCB), knowledge gradient (KG), entropy search (ES), and predictive entropy search (PES). BO focus on solving the problem maximize or minimize an objective function f of x. The following slides will focus on minimize f of x, since in NAS, our target is normally minimize the validation loss. The function f have several properties, like f is expensive to evaluate, so the number of evaluation will be limited. Typically, f will be evaluated to a few hundred only. F lacks known special structure like concavity or linearity that would make it easy to optimize using techniques that leverage such structure to improve efficiency. So, we can say f is a black box. When we evaluate f, we observe only f of x and no first or second order derivative. This prevents us from using gradient descent, Newton method, or quasi-Newton method. Therefore, we say it's derivative-free. In Bayesian optimization, we will use surrogate to model and predict f of x. The first and the most commonly used surrogate is Gaussian process. We will go through Bayesian optimization detail based on Gaussian process. So we can write down our data yi is generated from a Gaussian process FGP of xi, and the pseudocode of BO is as follows. First, we will place a Gaussian process prior on f. Notice that we have n data point in the beginning as the initial data set. And then we start the experiment iteration. First, we'll use the data we have to compute the posterior probability of f with Gaussian process regression, GPR. And then, based on the acquisition function, we will try to find the x that maximizes the acquisition function. So we will have an expected xn for our new experiment. And then we'll evaluate f of xn, and we will store this as yn. And we'll iterate this loop for n times. And finally, we will return the best solution we have with the smallest f of x. Because the BO algorithm is modeled by Gaussian process regression, we can write the prior and posterior down. Suppose at time t0, we observe our data sequence x1 to xn and our y1 to yn. We then write the prior distribution, the FGP of x1 to xn is a normal distribution with mean mu0 and the covariance matrix sigma 0. And then we want to infer the f of x at new point x prime. So we will, based on GPR posterior distribution, will be the probability of FGP of x prime given our x dataset x1 to n and y1 to n and our x prime. And this will be a normal distribution with mean mu n and the variance sigma n squared. And it's compute in Gaussian process regression. To compute the posterior distribution, we need to get the mean function mu0 of x and the kernel function for covariance matrix. The mean function mu are commonly chosen to be 0, or sometimes we can choose some low-order polynomial in x. Here the mu c is the hyperparameter and alpha I is also the hyperparameters. The kernel is chosen based on the problem and the data. For example, we can take a simple Gaussian kernel. So the covariance sigma 0 of x prime is the exponential of minus x prime squared divided by 2 beta squared. And here beta is also the hyperparameter for the Gaussian kernel. And if we choose a polynomial mean function and Gaussian kernel, we can use 3 approaches to find our hyperparameter set. The eta equals to mu c, alpha I, and beta. The first approach is maximum likelihood estimation, MLE. We maximize the likelihood of observation under the prior independent on hyperparameter. So the optimized eta hat is the eta that maximizes the probability of FGP of x1 to n given our eta. The second approach is maximum posterior, MAP. It considers a prior distribution for hyperparameter. Common choice of P of eta, including uniform distribution in a valid range, normal or log normal distribution. So the optimized eta hat is the eta that maximizes the probability of eta given our FGP of xn to x1 to n is equal to the eta that maximizes the probability of FGP of x1 to n given eta times the prior P of eta. The third approach is fully Bayesian approach. In this approach, we don't compute the optimized eta hat. Instead, we compute the posterior distribution on F marginalized over all possible value of the hyperparameters. So the posterior distribution given eta will be this marginalized over all eta. And this is hard to compute, but we can approximate by MCMC. Acquisition function defines the exploration policy for new observation. It guides us to find the next most promising unknown point to evaluate. We need to balance exploration versus exploitation in acquisition function. There are many different acquisition functions like expected improvement, upper confidence bound, knowledge gradient, entropy search, and predictive entropy search. UCB might be the simplest way to combine exploration with exploitation. And the acquisition of UCB, we can write it as a minus mu n of x plus the hyperparameter beta times the variance sigma n of x. With lower mean, it favors exploitation, and with high uncertainty, it favors exploration. So for a new x, we try to maximize this acquisition function. The next is expected improvement. It is the most common acquisition function. Suppose at t0, we have the best fn star. It's the minimum FGP of xi for all xi. After evaluating result at new x point, the improvement of the best value should be the expectation of the maximum value of fn star minus FGP of x prime, or 0. It means that if the new evaluated FGP of x prime is smaller than our current best f star n, then the expected improvement will be f n star minus FGP of x prime. But if FGP of x prime is larger than fn star, then the expected improvement will be 0. EI select the x prime that optimize the expected improvement. So the xn plus 1 will be the x prime that maximize the expected improvement, EI. With Gaussian distribution described previously, the EI can be written as fn star minus mu n of x times capital phi of fn star minus mu n of x divided by sigma n of x plus sigma n of x times lower phi of fn star minus mu n of x divided by sigma n of x, where the upper phi is a CDF and the lower phi is a PDF of Gaussian distribution. Now we rewrite the fn star minus mu n of x as a delta n of x. The delta n of x is the exploration part of the expected improvement, and the delta n of x is the exploration part of the expected improvement. So this function, it really describes how the expected improvement balance between exploration and exploitation. Notice that EI is easy to evaluate and implement, but it not works fine at noisy data. Knowledge gradient acquisition function is similar to EI, but it tolerates an uncertainty of final recommendation. The acquisition function we want to optimize is kg of x. It's equal to the expectation of mu n star minus mu n plus 1 star given x1 to n, y1 to n, and xn plus 1. You can see here we replace the expected value f of x in expected improvement EI with the posterior distribution mean mu. So the mu star is equal to the minimum value of the mean function mu of x given our training data x1 to n and y1 to n. And the mu n plus 1 star is the minimum value of the mean function given training data plus 1 extra observation xn plus 1 and yn plus 1. At time t0, suppose we have input data x1 to n and output y1 to n. The algorithm to compute the knowledge gradient acquisition function is as below. Let the mu n star to be the minimum value of the mean function mu of x given our training data xn to 1 and y1 to n. We estimate the mu n star minus mu n plus 1 star stochastically by computing it j times. First, we will generate yn plus 1 from the GPR posterior Gaussian distribution, and then combine our dataset with new generated data x, yn plus 1 as the new dataset to compute the mu n plus 1 and mu n plus 1 star. Then we can compute the delta equals to mu n plus 1 star minus mu n star. After j times, we average all j's delta to get the estimation of kg n of x. After we get the acquisition function kg n of x, we can find out the most promising x that maximize the acquisition function for our next evaluation. Notice that since kg considering the noise of each recommendation, the performance of kg is much better than EI in noisy data. Entropy search, ES, records the information of the location of the best solution according to its differential entropy, seeking to maximize information about location x prime. So we can write the ESN of x is equal to the entropy of T0 posterior distribution minus the expectation of the entropy to the T0 plus 1 posterior given f of x at x. It's hard to estimate ES due to no closed form for both terms with GP, and it is also required to evaluate a large number of y to approximate the expectation. The predictive entropy search, PES, provide an alternative to ES by using the mutual information to derive. So PES could be written as the entropy of the probability of FGP of x given our data, and this can be computed in closed form. But the next term, the minus expectation of the entropy of the probability of FGP of x given our data and xx prime, could not be easily estimated. Both ES and PS requires approximation technique result in different sampling decisions. We can consider surrogate function other than GP. For example, TP builds a model by considering good and bad groups. Here we will use the acquisition function EI to explain Bayesian optimization with TPE. We first rewrite the EI function as the integral of positive value of f star minus y times the posterior probability p of y given x. The f star here is a threshold value to separate good from bad groups. TP do not model p of y given x directly. Instead, it modeled by defining p of x given y. So we can write the p of x given y conditionally. If the y is smaller than f star, then we write it as L of x. If it's larger or equal to y, then equal to f star, we write it as g of x. And so for the L of x, it's a good group because we try to minimize our f of x. And the g of x is a bad group. Then we rewrite the EI of x as the integral from negative infinity to f star. F star minus y times p of x given y times p of y divided by the probability of x. And we can rewrite it by we set gamma equal to the probability of y smaller than f star. And we can get the p of x is equal to gamma L of x plus 1 minus gamma times g of x. And so we can rewrite this function as this. And we can approximate this function with gamma plus g of x divided by L of x times 1 minus gamma and take the inverse. This equation shows that the expected improvement is proportional to the ratio L of x over g of x. This one. To maximize the expected improvement, we should maximize this ratio. So we should draw value of the hyperparameters which are more likely in the good group L of x than in bad group g of x. TP works better for categorical and conditional inputs. After the introduction to Bayesian optimization, we begin our main topic today, AutoKeras. In this section, we will talk about the paper of AutoKeras. AutoKeras is an example using Bayesian optimization in NAS. It explored the network architecture search space through morphing. Network morphism is to transform an existing architecture to another through some predefined operations like insert or remove a specific layer, add a skip connection, or change the hyperparameter of a layer. In AutoKeras, the morphing direction is decided by 3 steps. 1. Train the underlying Gaussian process model with existing architecture performance. 2. Generate next architecture guided by our defined acquisition function. 3. Train new architecture performance and update performance metrics. Although NAS space is not Euclidean space that could be easily used for conventional algorithm, the author of AutoKeras designed a kernel for Gaussian process that is based on the edit distance for morphing network to another network. We first reframed the NAS problem into a Bayesian optimization problem. Given a neural architecture search space F, the input data D is a union of dtrain and devalidation, and evaluate metric cost function is a cost. Then we want to find the optimal neural network F star. The F star is the network F that minimizes the cost on our validation function. So the cost is in fact the unknown objective function we mentioned in Bayesian optimization. And the F here is the input value, or X, we mentioned before. And the theta star here is the weight that minimizes the loss of training data. So AutoKeras use Gaussian process as surrogate function. The cost is generated from a normal distribution with prior mean and our prior covariance kappa 0. And the kernel here is defined by kappa 0 FA, FB of two different network FA and FB is equal to exponential of minus rho square of D of FA, FB. The distance D of FA, FB is the edit distance for two networks. And the rho here is a mapping function from Bayesian theorem. Bayesian theorem is used to map metric space to an L2 space with distortion order of log n. This ensures that the kernel is positive, definite, and valid. We want to calculate the exact edit distance, but it's NP hard. So we approximate the D of FA-FB with two edit distance. One, the DL. It's called the skip connection ignore morphing distance. And two is the DS, the skip connection only morphing. And the lambda here is a hyperparameter that balances these two different distances. AutoKeras use UCB acquisition function. So the mu is the posterior mean of our cost, and the sigma is the posterior variance of the cost. Here is the algorithm for AutoKeras. First, we have our input history. H is the search history, so we will have some network Fi and its corresponding trend weight theta I and its corresponding cost Ci. And R is the temperature decreasing rate, and T low is the minimum temperature. And then we assign T to be 1 and assign a priority Q. Then we assign the lowest cost in our history to be C mean. And we push every network in our queue. Then we iterate the loops until we have no network in the queue or reach our minimum temperature. So we assign T to be T times R, and we pop one network out of the queue. And then we do the operation, morphing operation, and try to run the Bayesian optimization. So for each operation here, we will morph the network F into F prime. And then we randomly choose whether to push the F prime into our queue. And then if the cost of C prime is smaller than C mean, then we assign the C mean to be C of F prime and F mean to be F prime. And we iterate this process until we find the best network F mean. AutoKeras consider 4 types of neural network morphism operations. The network morphisms start from a simple computational graph G. Those operations are inserting layers, widening node, adding connection, and adding concatenate. Inserting a layer to G at node U can be represented as operation deep G U, where U marking the place to insert a layer. Widening a layer U in G can be represented as operation wide of G U. Note that since the width of U is changed, both input and output layers should be defined accordingly. Adding skip connection in G from U to V can be represented as operation add of G U V. We need 2 pooling layers that process output U to the same shape of input V. Last, adding concatenate connection in G from U to V can be represented as operation concat of G U V. Due to the concatenated tensor is wider than original, we need extra layers to reduce the width back. Previously, we've mentioned that edit distance is approximate by the combination of a skip ignore distance dl plus a skip only distance ds. We will now check the details about how to calculate dl and ds. To calculate dl, provided we have 2 networks, FA and FB, for each layer in FA is LA equals LA1, LA2, and for each layer in LAB is LB1, LB2. And assume that the total layer of LB is larger than LA. First, we try to align topologically by matching the layer in topological order. For example, if LA have 4 layers and LB have 5 layers, we try to align each layer. And then for each layer, we combine the aligned layer and we can measure the distance difference between each layer. So the dl of LA LB is equal to WLA minus WLB divided by the max of WLA and WLB. The WL is the width of layer L. So for example, if at the same layer for LA, the WLA is 2 and WLB is 3, so the DLA-LB will be 2 minus 3 and take absolute value, so it's divided by, so it's like 1/3. And then, because we still have some layer that is not matched, so we leave this into here. We just use the larger LB to minus the smaller LA. So you can see that for those not matched, the distance, they will contribute more. Because for each layer not matched, it will contribute 1. But for those matched, it will contribute less than 1. And here we show in figure how this works. For example, we have 2 layers FA and FB, FA with 3 layers and FB with 4 layers. And we've tried to topologically align each layer. And then we try to widen the layer to make sure every layer is matched. But we still left 1 layer not matched. So we insert the extra layer. And then FA will match FB. So here, the not matched layer will contribute 1 because they have like 1 layer not matched. And for the rest, we will add every difference. For example, for the first layer, it's 1 divided by the max 10 and 11, so it's 1 divided by 11. And for the second layer, it's 6 over 1. And for the fourth layer, it's 8 over 1. So we add it all together, we can compute the DL. But since there are multiple morphing paths or matching functions that could do FA mapping to FB, the authors, they propose a dynamic programming that minimizes the added distance of DL of LA-LB with a matrix A, LA cross LB. With the matrix A, we can compute the smallest morphing distance of DL, LA, LB. Next is the added distance for skip connection only. Skip connection only distance consider layer pair set SA1, SA2, etc., where the SAH is equal to the pair of LAI and LAJ. The added distance of skip connection only is also consists of two parts. The topological aligned distance between SA and SB, it is ds of SAD, phi s of SAI plus. And the not aligned part is the absolute value of SB minus the absolute value of SA. Due to the lack of a free and good NAS tool, the author of AutoKeras developed an open source AutoML system focused on NAS. Their target is to design an easy-to-use system that can deploy locally without extra cloud service cost. To efficiently utilize CPU and GPU, AutoKeras run the search algorithm on CPU, while the model trainer is computed on GPU. The API design follows the classic design of scikit-learn API. The graph here shows the workflow AutoKeras system. When user initiate a NAS for a dataset, the API receives the call and then preprocess the dataset. Next, the API will pass it to the searcher to start the search, and it is run on CPU. The Bayesian optimizer in the searcher will generate a new architecture. It calls the graph module to build the generated architecture into a neural network in the RAN. The new architecture is copied to the GPU for the model trainer to train with the dataset. The trained model is saved in the model storage, and the performance of the model is then feedback to the searcher to update the Gaussian process model. After describing the algorithm and system setup, we will show the experiment result. In the paper of AutoKeras, the author trained and tested NAS on 3 benchmark datasets. They are MNIST, Cypher10, and Fashion. The initial architecture is a 3-layer CNN with 64 filters at each layer. To test the NAS performance of each algorithm runs totally 12 hours on single 1080 tie to find the best architecture. In order to fairly compare the performance of each neural network, the author decided to train each neural architecture for 200 epochs in all of the experiment. The table shows the performance comparison for different NAS algorithms. The first 2 methods, random and grid, are baseline. SPMT and SMAC are conventional cache and HBO methods. Seeds and NASBot are common NAS algorithms. The rest are different AutoKeras algorithms. You can see that the full version of AutoKeras, AKDP, have the lowest error rate on 3 datasets. The above figure shows that the evaluation efficiency of different AutoKeras algorithms. The BFS is AutoKeras without Bayesian optimization that shows the worst search efficiency. BO is the AutoKeras without morphism that have similar efficiency in respect of number of search models. But since the training efficiency is less, the full version AutoKeras less than the full version AutoKeras AK, the overall efficiency is less than AK. The below figure shows that the influence of hyperparameter beta and lambda to the algorithm performance. It requires some proper beta and lambda to have better AutoKeras performance. In the end, we will introduce to the open source library AutoKeras. Data Lab developed AutoKeras. It is an open source AutoML system for NAS based on Keras. You can easily pip install AutoKeras with very few requirements like Python above or equal to 3.5 and TensorFlow above or equal to 2.3.0. And it is also easy to write code for AutoKeras. Before version 0.4, the code is implemented based on the description in their AutoKeras paper. However, after version 1.0, AutoKeras they deserted skip connection and morphism operation and changed the auto-tuner design based on Keras tuner. Keras tuner worked as a hyperparameter tuner for NAS. User can select the optimizer and optimize the networks from a predefined hyperparameter space. The key difference between AutoKeras and Keras tuner is that AutoKeras hypergraph stores the overall search space containing both the preprocessors and hypermodel. Therefore, AutoKeras fine-tune the hyperparameter of preprocessor and architecture at the same time. There may have several reasons why AutoKeras changed their design. Reasons like it would be better for integrating code, it is easier to use or modify code. The mechanism of morphism might introduce arbitrary complexity that require extra mechanism to work without overfitting, just like the mechanism in the AutoML system teapot. Or it could reduce the search space for real application by focusing on meaningful hyperparameters in different tasks. You can build a customized neural network using the building blocks in AutoKeras to assemble neural architecture and then use the AutoModel API to fine-tune the hyperparameters. It is also possible to extend blocks class, override the build function of the block, and make AutoModel work for the customized block. Next, we will go through two basic examples. The first example is image classification with MNIST. So we download MNIST data and split into train and test data. Then we'll create a simple neural network architecture by stacking image input on image block. And finally, a classification head. The image input is the image input preprocess block in AutoKeras. And the image block is an image CNN block in AutoKeras. If we don't assign any block type, it will select and tune automatically from ResNet, exception, or vanilla CNN blocks. And then we call AutoModel. AutoModel we'll learn the hyperparameters of the neural networks. Here, we will test the architecture training 20 times. Then we will run the auto-tuning process by call the fit function. For each test, we run the training for 3 epochs. In the end, we output the final best performance model and save the model for further use. Here, you can see the training process. In the beginning, you can see that we don't have the best architecture in the first trial. And then we train our first trial and found the validation loss is 0.24. And after iteration, you can see at trial 10, we have some best performance model architecture, and the best validation loss is 0.05. And then in the end, at 20 trials, we've seen that the best performance changed and the best architecture also changed. And the best performance validation loss now is 0.38. The second example is text regression with IMDb data. The function IMDb role is for downloading and preparing dataset. The input X should be a list of strings, and output Y can be labels one-hot encoded or binary encoded. Then we use the AutoKeras text regressor to handle the overall preprocessing and auto-tuning for text regression. The text regressor will choose from several types of base model, including vanilla, n-gram, transformer, and BERT. Where vanilla is for basic embedding plus a convolution plus a dense block. N-gram is for n-gram vector plus dense block. Here, we will test the architecture training 30 times. Then run the auto-tune process by call the fit function. For each test, we run the training for 5 epochs. In the end, we output the final best performance model and save the model for further use. You can see that in the beginning, in the first trial, the performance for validation loss is 0.15. And at the 10th trial, we have our best performance. The validation loss is 0.83. And at 20th trial, the validation loss drops a little bit to 0.834. And in the end, at 30th trial, the validation loss dropped to 0.82. Okay, so finally we'll make a remark on AutoKeras. AutoKeras is an interesting example of how AutoML solution evolved. The original concept of AutoKeras is NAS with morphism search space, defined by the metric distance of 2 neural networks, and use Bayesian optimization as the search algorithm. After developing for years, they've changed the direction to NAS HPO with Bayesian optimization. They started over the code base based on Keras tuner. Personally, I think an AutoML solution is always trying hard to balance lots of different concerns, like coding efficiency, code transferability, whether it supports our target language, how this tool can help in which project phases. Speaking of this aspect, the original AutoKeras was more like a NAS fine-tuned toolkit with network morphism mechanism that might be helpful to improve marginal performance. However, current AutoKeras works more like a fast NAS prototype tool that helps users to find acceptable baseline model performance in early stage. The rest of concern are whether it supports candidate models or learning efficiency, etc. So, we may not find the best AutoML solution, but only tools that fit in our specific tasks. Okay, that's all. Thanks for your attention and wish to see you in the next video. Bye bye.